Hello.
Hello.
Oops. Okay.
Yeah.
Can you guys hear us and see what's happening? Okay. Yeah. Apparently you can see. Can you hear? Can you hear correctly? Metal Snake is here with me, and we're going to continue what we were doing last week. So yeah, haven't been streaming for a complete week. Um, like I said, I won't be streaming more than once a week currently, probably. Maybe twice a week if Metal Snake is available and we are, you know, in the mood. Uh, so yeah, for now it's once a week, every Tuesday, at least. And last time we were working on the memory allocator. Uh, let's see. Okay, so yeah, we started writing the memory allocator module. Any updates? Yes, I wrote a couple of changes, very small changes, by the way. As you can see, so it's basically typos and comments. Yeah, and here, yeah, I refactored very slightly what we did. I added missing functions. There was a to-do entry somewhere. Let's see.
The refactor. There we go. Yeah.
Mm, I don't see the to-do entry. It's probably still here then. Okay. And yeah, some comments. So now that we have the structures, yeah, salut brute. That we have the structures, we're going to write the allocation. But yeah, before we begin, uh, as usual, you need to update your own copy of the code, and then you will start working.
Forget what it's called. Was it R Brown? I believe. Git pull R Brown monster.
Yeah, it's so if you want to check remotes, that's the command you should use.
Ah, that's the one.
So I think it's pull repository branch. It's usually in that order. Okay, then you can push, well, now or later, you can push that on your repository. Let's make sure that everything builds and runs, so that all things related to the infrastructure are, done. Okay. Oh yes, I changed that too. That's right. I told Grub to actually use the console too. So it's a very small change. Um, okay. I think it's a good thing because it helps people realize that there is a bootloader in between the starting of the virtual machine and the kernel code. It's not all magic. Okay, so let's continue the mem module. So just one thing, please. Let's have it like this so that we can
Oh,
really
that's
see as much as we need.
and let's have the uh for the another one like the virtual group. See how that works. Um,
What do you want to do?
tab group, was that it? Yeah, there we go.
Okay, but can you actually move? Like, can you actually have the same file on the left and the right? I don't think you can. Yeah, no, I don't think you can.
Hmm.
Anyway,
Oh
um,
well.
so these are the structures we currently have. If we need to change them, we will change them. What else do we need? We had the link last time. Let me see if I can find it. Very nice colors. uh, let's see. We had an image, or maybe I found it with Google. Yeah, maybe. We had this too, but I'm not sure that this is Well, maybe it was. Maybe it was. Yeah. Okay. So this is going to be our reference. There are multiple um, algorithms discussed here. What we want to implement is one list, so no segregated list, just one list, but with boundary tags and merging. So free list pointer 2. Yeah, I think it was before that, since it's the end already. That's probably it, keeping track of free blocks. So this is basically what we have. The first, well, these are words, so actually we don't really know what the blocks here are. And I'm going to call them the, I don't know, the cells, really, because we, like, the block is all the gray thing here, that's a block. The white thing here is another block, which is free, I assume. So yeah, we use this method here, explicit list among the free blocks using pointers. So we basically have a linked list of free blocks. Allocated blocks are obviously not linked, they are relinked when they are freed. And so we don't use multiple free lists and we don't sort them. We have a single list for simplicity. So this is the free list. This is one block. And in a block, we have a header boundary tag. And at the end of the block, we have a footer boundary tag, which we may rename if the names are not. Like, for now, we're going to keep that, but in the end, maybe we'll decide something else. We have a heap. And for now, what we do is that we initialize this heap as a single block that is then added to the free list. So basically, we have a single big block which is free and in the free list. So now what we want to do is to implement memory allocation. We want to take, like to create a new block, actually two blocks. We have one block, we break it in two. One is going to be allocated, and the other one is going to be added in the free list in the place of its of the previous free block. Basically, that's what we want. And we may not need that. Like, if we find a block that can't be broken down, we just return the whole block to the caller. That's basically it. And Metal Snake is going to code allocation, and at the end of the stream, depending on the time we have, I'll be writing the free code, mem3, or maybe next time, we'll see. Okay, so you're up.
In this, um, in this overview, it doesn't necessarily show you have header tags and footer tags, though. Is
Mm-hmm.
there?
Yeah, no, they don't. It's not necessary.
Okay.
We use boundary tags here because they help merging.
Okay. So you can see which are the block. Like from here, you can quickly see.
Yeah. When you free, look at the free interface. When you free, you just give a pointer. And so from this pointer, you must retrieve all the data necessary to know the block before, the block after, and everything you need to merge them if you can. So without boundary tags, it's not easy. Some allocators don't work that way, by the way. Some allocators don't merge. They just provide fixed sizes, and when you free, you just free a block, and that's it. The block just gets added to a list somewhere, and because of where it comes from, you don't need to merge. Like the slab allocator, for example. This is the case with most stacked allocators. Here, we make something simple. There is no stack of allocators, so we can't really rely on what provides us with memory, because this is just a single big block. So we'll have to merge blocks, basically. If we don't, we'll have fragmentation problems. So we could afford not to free, not to merge, like I said last time, but I don't think I don't think there is really any strong reason not to do it, because it's basically the reverse operation of breaking a big block into two smaller blocks. So it's not that difficult.
let's see. The when allocating uh, you want to see the only parameter you give is the size, just to see how big of a
Mhm.
block you need. Uh,
So this is the size of the payload. Okay, that's important.
mhm. And you add onto that the size of the boundary tags as well as um, uh, the list or
Well, why would
that
you add
the
the size
pointers
of
or
the header? It's actually its name.
the header. Sorry, yeah.
Why would you add the
Um,
size of the header?
well, it needs to. That's the minimal size it needs at least,
Okay,
right?
okay. So for people to follow, um, yeah, it's really annoying not to be able to use this.
Exactly. Yeah.
Can't we do it?
Maybe.
Really, can't we? Let's take a look quickly because it's really. Uh,
Otherwise, for next time, I'll have a quick look at other text editors. I don't necessarily use gedit, uh, but
that's how they do it. Right. We can drag it. Yeah, okay, in another JDit window. No, okay, so there is a plugin apparently. Multi-edit. Do we have that? Can we install plugins? Yeah, sorry guys, but I feel we're wasting a lot of time without that kind of feature.
a lot of scrolling back and forwards. Yeah.
Multi-edit. Okay, and I suppose we don't have anything to download it quickly. Uh-huh. This one maybe? Yeah. So I'm gonna close. Did you change anything?
I did not. No.
Okay. So probably you mistyped something on the keyboard. Yeah, what's slowing the process down is my disk. It's not an SSD. But it's still very fast. Okay. So preferences, plugins, multi-edit. Okay. Now let's open that and tab group. Okay. Does that work? No. How do we use it? Multi-edit mode. Okay. Whoa, whoa, whoa. Okay, sorry guys, I'm gonna take just 1 minute to see how this is used. Control Shift C once enabled, you can start inserting edit points manually. Control E, Control Home, Control End. Really? That's not very user friendly.
Not sure if this actually is what we're looking for.
Yeah, maybe. Okay, we've wasted enough time. Yeah, it doesn't
Yeah. Let's
work.
just.
Whoa, whoa, whoa. Multi-edit mode. And this one needs to be in multi-edit mode too. That doesn't work.
Maybe if in
Does
a new
someone know this
window.
plugin, by the way? Just in case. Multiple edit points by which you can simultaneously document in multiple places.
Maybe if we open two instances of gedit and then
Yeah, I guess we're going to do that, but it's annoying, really. So it's what, new window, this, basically. Ah, please learn something like Vim or Emacs, something that actually does the job.
yeah.
And I'm not talking to you in particular, I'm saying that out loud, talking to everyone. Okay, so we'll have to reload, I suppose, but okay, now we have the structures here, and we'll have the code here. Okay, so we have a block, and inside the block we have a header boundary tag, which is made of a boundary tag, and right after it we have a header. So basically, if we use this set of slides here, do we have one that correctly represent? Yeah, it's that one. This is basically what we have. The size, an allocation flag, and only when the block is free, the next and prev pointers of the free list. So obviously here, if a block is allocated, there is no need for it to be in a linked list, because that is going to be used by the code that actually made the allocation. So these pointers are only relevant if the allocation flag here is cleared. Okay, your turn now.
Um,
So,
question: Why
yeah.
in a memory block is there only a header tag? Why does that not contain the footer tag as well?
So yeah, you might wonder why not directly use the header boundary tag. It's pure semantics. The header boundary tag represents the beginning of a block, whereas the block represents the whole block. That's the only difference. It's a difference in words only. So, for example, if you have a block, you might have functions such as this one, get the footer boundary tag. It makes no sense to ask for the footer boundary tag of a header boundary tag. They're separate objects, there is no direct link between them, but a block which contains them logically also contains the footer boundary tag. Does that answer your question?
Mm, not entirely, no, because this is the header boundary tag, but
Mm-hmm. Yep.
um, it doesn't have this footer tag
No, it
in the
doesn't.
block.
It doesn't because the size is variable. Structures are the layout of structures is determined by the compiler at compile time. But here we have variable sized blocks. We can't know their size in advance.
Oh, right.
So
Okay.
again, the difference is purely logical.
Okay.
Like it's just words, semantics, nothing else. The compiler doesn't know what we're doing. And that's why this kind of exercise is very interesting for you, especially in C. Actually, I know one school in France that I don't know if they still do it. The best computing school in France used to ask new students to write a memory allocator, and they wouldn't say because it's like illegal, but they would only select like people who did it or who made a good attempt. This was a way to select good students because they realized that what made a good school is actually not having good teachers; it's having good students. So that's how they filtered on entry using that kind of exercise. Write a memory allocator because it means you can use pointers. It means you know how to manage size, variable sizes. Uh, that you have that clear picture in your head. And I'm not at liberty to say Blut. So, uh,
Mhm.
well, I am, but I don't want any trouble. Okay. So, so yeah, it's really a good exercise of pointer manipulation. And keep in mind, a pointer uh, points to an address, and when you abstract that, what you get is a reference refers to an object. You basically say the same thing, but at different layers of abstractions. So, well, layers of abstraction. So here, when you see a block, you shouldn't think just in terms of structures like you see them in the code. You should picture them in your head, like this, exactly that. And this part here, well, actually all this has a variable size that is given here. This is the picture that you should have in mind, which is why I keep it nearby, so you can quickly reference it. So what I wanted you to do before we start writing code, because writing code is actually quick, I would advise you, like not only you again, you in general, to always know what you're going to code before you write it down, unless you're writing a very experimental prototype. So try to tell us what you're going to do with normal words. Try to use the words we already have, because we don't want to have synonyms, they create ambiguity. And we'll see if things are missing or not.
Okay. Um, well, initially, I guess at first you need to see if the size actually fits. Well, that's the entire thing of memory allocation, of course, to see if it fits and then actually allocate it. But you,
Do you really
um,
need to do that? There is another way
well,
to do it. If you don't have any block of well, any block that can satisfy the requested size, then it's fine. You return null and you're good. You don't need to check it actually. If the size is too big, your lookup algorithm will return no satisfying block,
okay, yeah,
so
yeah,
you don't need to check the size. But that's for a bigger size. What you need to do instead is prevent that the size be too small.
yeah, yeah,
So that's
because
not actually, well, you will have to check, but actually you don't necessarily have to check. You could directly align it to a suitable size directly.
okay.
Um, does that make sense? I think here you need
Mm,
to check it. You're right. I don't think we can just have the same code applied on all values that would yield something sane. So yeah, we'll have to check.
to see if it's actually
Hmm.
larger than the next and previous or the
Yeah.
list
Okay.
object.
So that's one thing. What are you going to do next?
Um, check the boundary tags if uh,
Check the boundary
or
tags.
yeah, exactly, yeah.
What boundary
What?
tags?
Well, you start at the beginning of the block or
No,
the heap that you have.
no, you don't.
No.
You
Oh,
start at the free list. And for now, for that thing, I'm going to go back to the other slide, and
yeah.
it's a pity that they're not side by side. Um, yeah, I missed it. It's this one. Now here, this block is already free, which is a shame. Imagine that the only free block is this one. You don't want to check this one, and then this one, and then this one, and oh yeah, okay, it's free, I can try it. That's why we have a free list. So you directly jump to the first free block and you test that.
Oh yeah.
And that's also why you have, for example, segregated free lists, because then they are sorted. Well, usually they are sorted by size, which means that you directly know that any free block in that range of sizes would satisfy your request, for example. and you have multiple policies, like to avoid fragmentation at the cost of more lookups for a single size, or on the contrary, to have a guaranteed constant time lookup, which will give you the first free block, but this block might be twice what you need, so this will create fragmentation, for example, and you decide what policy you want, depending on your needs. So here, again, we don't have that kind of complicated things. We have a single list, but still, we want to only check free blocks. So the first thing you do is check your free list. So you basically grab your blocks, your free blocks in that free list one by one, and you check whether they satisfy your request or not.
Okay. That yeah, that makes sense. Uh, so you grab the first block that actually fits the size,
Yeah.
I guess.
So one thing when you say these things, you say the first. Try to generalize it immediately. So you have two steps here. The first step is walking over all the blocks, and another step is checking one block, whether it's the first or not. And unless there is something special about the first, which sometimes happen, you don't need to think about the fact that it's the first or not.
Sure, yeah, but you get a block from the free list,
Mhm.
which I mean, it doesn't necessarily have to be the first one, but yeah, uh, you get the
That's
first
exactly
one
what I'm
that is
saying.
available. Yeah, you get the first one that is available to you or available for that size.
Well, you have to start. So yes, there is
Okay.
a first, but don't make it special
Yeah.
unless it
Yeah.
needs
Okay.
to be.
Okay. Um, and after that, you uh set the boundary tag that it is allocated,
You
and
set. So be very careful about your words because this is the only thing I can listen to. I can know about what you're thinking. You have
um,
a block. What do you do with this block?
um, well, you have the boundary tags which contain the allocated bool, which you have to set to uh, true.
Do you really have to
Since
check the allocated flag when you are working a free list?
no, you don't have to check it, but you have to set it though. You
Oh,
say that
you
it
set
is
it
allocated.
allocated right away. Um, okay, you're going too much into the detail. Um, why do you want to allocate it? Why do you want to set it
If
allocated?
is this sorry, is this after we get a block that is actually the proper size, or is this?
I don't know. You tell me.
Oh, well, I,
Be explicit because
I
I can't know what you're thinking. I can
okay.
guess, but I don't want to guess. The compiler is not going to guess.
You for allocation, you get blocks, or you get a block, or you iterate over the
So okay,
uh
we have done that part. We iterate over the
yes.
block. What do we do for one block?
You check the size,
Okay, check the
see if it
size.
fits.
Okay, you see if it fits. Okay, so two possibilities: it doesn't or it does.
If it doesn't, then you keep checking to see if there's a
Okay,
block in the free
that's the
list.
easy one. And
Mhm.
I'm going to use the occasion to mention once again, I've said it many times, but I'm going to say it again. I strongly suggest that you check errors first, because this way you will have them handled, you will not forget. And second, because they are very quick to handle. So, and there are other reasons that make the code more performant, but I won't go into details. Yeah, check errors first, and then you can focus on the real nominal case that is interesting, where most of the work is going to be. So now we have the other case where the size matches. So what does that mean? That the size is, well, matches maybe not, but the size is, uh, what word could
But
we use? Uh, adequate?
yeah, it's either
Large
greater
enough?
or yeah, greater or equal to
Greater or
the
equal to.
size.
Okay, so
Exactly.
what are the possible cases here?
To how do you mean to what we should do in this
Well, you
case?
just said equal or greater.
Mm-hmm. Well,
Are
if it's
those the only cases?
after, well, if it's not less, then it's either greater or equal to,
Yeah, but I mean,
right?
what do you do in that case?
If it's equal, then you don't have to um, break that into smaller
Okay.
blocks. Um, and if it's greater, then you do have to set additional boundary tags.
Are you sure?
That's what I thought.
It's going to be the case most of the time, but there is a catch. You break your block into two blocks. Each of these new blocks must have the minimal size required. So for example, if the block you found is like 4 bytes greater than what you need, you're not
Oh.
going to be able to break your block into one big block and one of only 4 bytes. You won't even enough room for the boundary tag there.
Mm-hmm. Yeah.
So
Okay.
you have to take that into account as well. There is a size below which you cannot break a block into two. So below that size, the best thing to do is to just return the whole block to the caller.
Yeah. Yeah.
So it's not equal, right? It's if it's below that threshold that we have to compute. But it's easy to compute. Like you can make a macro of it.
Yeah.
Actually, we could even do that right now. But we could
At a
we could
minimum
just write
size.
the name of the macro because we don't need the value. The value is going to be easy to compute. It's just additions of size off. It's really easy. But we need to remember that that tricky detail because that's where this is precisely the kind of situations where you're going to have bugs. So in order to avoid bugs, you take precautions. And one good way to avoid bugs is with good names. So yeah, block min size. So this is the size of the block, right? Not the payload, the full block. That's
Um,
important too.
yes. So that's including the boundary tags and including the
The header.
header.
Yeah. Okay. So very yeah, that's good. Okay, we can leave that there. Uh, like the way it's gonna work is like this. If you forget what we just said, you're going to code and then you're going to see that macro that we talked about, and you're going to remember, oh yes, that's right. And you're going to wonder, like even if you forget that discussion, you're going to wonder why is there a min size macro instead of just checking if the size is equal, which is the the obvious uh, simple thing to do. And so this is where a comment might be good too, because this is maybe complicated enough that it needs description. But I'll do the comments.
Okay.
Okay,
Um,
so you have a block, you check against that size, then if if it's below that size, you just return the block. Okay, so you need to remove it from the free list first. You need to set the allocated flag, all those simple little things that we can just like they're details. We don't really care about them. And then the interesting case is the size is bigger than this threshold. So what do we do then?
uh, well, like you just said, it has to be bigger than the that minimal size, including the boundary tags and header.
Hmm.
And if it is, then you you'd have to allocate another block or add another block to the free list. I mean,
So yeah,
initialize
we
that
have one
block.
block. We're going to break it into two. The first is
Hmm.
going to be returned, and the rest is going to be added to the free list. So in order to make the code simple, what we're going to do is that we're going to systematically remove that big block from the free list first. And so either it's entirely given to the user or a smaller part is re-added later.
Hmm?
Okay. What else do we need to take care of? Um, yeah, the size that is given to Memalloc is the payload size. It's a lot simpler if we don't have multiple, types of sizes. So what I suggest is that you always use block sizes, full block sizes, so that there is no confusion between payload size and block size.
Okay.
Anything we need to take care of? I think it's fine.
But then, as the user, you'd want to. The only thing you want is really the
Yeah,
payload, so you'd have to
we can't
handle that
change
yourself.
the interface,
Yeah.
but inside our own implementation, we decide about those details. This is
Yeah.
encapsulation; it's not exposed, so we do what we want. But the first thing I suggest you do is convert the size into a block size. And this is also where you might want to check that block size against the minimum block size, and then increase the size if it's below it.
So, sorry, that
Yeah, the size
adds
here.
it to adds that to a block size, or
Yeah.
call that a block size.
No, no,
How do you mean?
it's the you can leave that as just size because that's the interface. It's the payload size, okay? But then you
Mm-hmm.
can just convert it into a block size, and you would write a function for that. Isolate your problems.
To block size, I guess.
Yeah, you could call it, well, convert to block size,
Convert.
or I don't know, payload to block. Payload to block size. It doesn't really matter. Like, take one. Honestly, as long as it's like meaningful enough, it's okay. There are multiple ways to do it. Okay. So I really suggest you do not do that.
Do what?
Uh, Update your arguments like this. What you just created here is what we call an in-out argument. The pointer points to a value that is used as an input, and on return has an output value. It's very confusing. Sometimes it's okay because the whole interface is like complicated, and it will not add that much complexity. Like, people will have to care, but very often this leads to mistakes. And the compiler is also much better at optimizing pure functions, functions which have no side effect. So yeah, I suggest that you just wait, no, stop, wait.
Oh.
I'll do it. Very simple, like this.
Ah, okay.
See, you don't need an additional variable, and you have no side effect. Functional programming is quite limited in what it can do. But if you need, like, if there are some things to remember from functional programming, is that you really want to have as many pure functions as possible. Pure functions being, again, functions that have no side effect. And the reason why you want that is because pure functions are immediately thread safe. Uh, they can be run in parallel, so they are really suited to distributed jobs automatically, and they make your they make your code just safer, simpler. So if you can, use pure functions. Well, write pure functions.
Uh, will we then here use a assert to check the size?
Do we really want to do that here? Like, convert to block size could do it itself.
True. Okay. Yeah. Um, so then
So
we
just quick question: if the size is 0, what do you do?
uh, you return null because you don't
Okay,
have a.
so let's check, because you have, like, consider this um, a good thing that these functions are already specified and well specified. So if size is 0, then malloc returns either null. Okay, we could do that, or a unique pointer value that can later be successfully passed to free. So we could do both. We could decide to return null, but we could also decide to allocate, like to have size 0 translated into, well, converted into the minimum block size and return a block of the minimum size. We could do that. Both are okay with regard to the specification. So you decide.
Okay. Hang on. So you return a unique pointer to where exactly? Does that vary, or
What? Ah,
does
well,
the
yes, a unique
return?
pointer. I mean, malloc is supposed to return a unique pointer.
Mhm.
So it's basically you handle size 0 the same as the size of the minimum block size. Well, the minimum payload size really here.
Uh,
I'm not saying that it is what we should do, but the specification allows us to do that, to return an empty block basically.
right. But if there are no, oh, okay, yeah. So then it gets a block from the free list and
Yeah.
returns that. You mean? Okay.
Well, it
Okay.
allocates something. That's all.
Yeah. Okay. For some reason, I was thinking if the free list was full or something.
No,
I'm
no,
not sure
no, no.
why. So here we check the size, I guess, against the macro, the minimum size.
Well, again, that should be done in convert to block size because that function is really, about block sizes. But
Right.
what you could do is check the size against 0. That's your decision.
With uh, well, if you assert it, then it just breaks if it is 0. Um,
So wait. You already have a block size here.
yeah.
The only thing that is allowed to be 0 is the requested size. I mean, the only uh, the question here is: do you want to return null or an empty block when size is 0? But the requested size, not the block size.
Um, I I'd suggest returning null because then you see that
Okay,
you're.
then do it.
Uh,
Okay, so that's my problem. You're testing the block size here, not the requested size.
you do that before.
Yeah, it's important to care about those details. And you see, that's why I want you to avoid confusing block sizes and payload sizes, because otherwise it's going to be a mess. Okay, so you convert to block size. Again, don't start coding that function right away. Finish the function you're coding now. You know what that convert to block size function is going to do. Okay, you don't need to write it. You know that what it's going to do. Just finish the function you have right now, and later we'll implement the functions that are missing, one by one.
Okay, so we get a. We need to get a first block from the free list or a block from uh, free list.
Sorry, I wasn't listening. I was replying on chat. What did you say?
We need to get or then get a node from the free list.
Well, no. The first thing we need to do is iterate over the list, and then for one block, we'll write some code.
Uh, so
We don't
how?
just. It's important that you say it, like saying things is really important because they show how you think. I don't want you to think that you want to grab a block. I want you to think that you are walking over lots of blocks, and then for a single block you're going to do things. Okay, these are two separate problems.
Um, and how to iterate over is do we check it against null for the nodes?
Oh,
I'm not sure about the.
there is a library. It's a list library. At the bottom, you'll find the iterator functions. Well, macros really. Oh wait, yeah, these ones are a bit complicated. Take the mouse. The LLC's variants are for lockless synchronization. So it's really these ones. And the
Ah,
one you want is really entry. That's the one. Now, careful because you see, here we have entry safe, and here we have entry. So this one is different because the node cannot be altered during the loop, which means that if you use that macro, you cannot remove the block while inside the loop.
which is not what we're looking for.
Well, it depends
Or
because the way I see it, we're just going to use that to look up a block. So once we have found it, we just exit the loop, and once we're out of the
ah,
loop, it's okay. But it's a classic problem modifying what your iterator. Like if you remove your iterator and then you ask for the next entry in your list in your container, because you have broken the link, you can't find the next entry. It's a classic problem. It's not.
yeah.
It's like you're going to find it in all languages, all frameworks, uh, unless they always have some temporary variable to take care of that case. But it's unlikely.
Okay. So we don't alter it in the loop. So just get it and then get out of there.
Okay. So again, I would not advise you to do it directly in the allocation function. What you should only like the allocation function is a high level macroscopic function that just assembles smaller functions that we call primitives. So here what you want to do is find a free block of that size. So basically you write a function find free block, something like this, and you know what it does. You know that it walks and it tests, etc. You can write it later.
Uh,
Also, just 1 second, I'm going to take the mouse again. Sorry for the interrupt. For Friedemann. So, very quickly, the white stuff here is our free blocks. Okay, the gray stuff is allocated blocks. So what we want to do is have a linked list of free blocks. And then inside those blocks, the view we have is this one. So this in purple, well, it's pink actually. In pink we have a boundary tag. So this is the header boundary tag, this is the footer boundary tag. And then if the block is free, we have a header that contains linked list pointers to to those other free blocks before and after.
um, and the this is what we return is the structure of a memory block, I guess.
I guess
The
so.
type.
You can also declare your variables after, like uh, like the functions. Write your variables and the compiler would tell you if they're missing anyway. So you can just declare them afterwards.
Okay. Um, and then
You need
arguments for that one.
arguments. Yeah, like we said, we don't really want to. So it's F list, but yes, we don't really want to have too many singletons. Basically, global variables. We want our functions to avoid directly referring to global variables. So we pass those global variables as arguments. So the day, for example, if you implement someday you extend this implementation into a segregated fit allocator, you will already have your free list. and you'll have multiple free lists, and all your code is going to work because it didn't assume a single free list.
Oh, yeah. Okay. Sorry. I had to go over that in my head, but that makes sense. Yep.
And don't worry, I'm going to repeat that and repeat that and repeat that all the time. That's how it gets. That's how it sinks in.
Um, so then we have a free block, and then we need to check it against
Are you
size, or
sure?
actually
Are you
that's
sure you have a free block? The first thing when you return a pointer, that pointer might be null. Well, and the first thing you should think about when you do something is that something might go wrong. Can something go wrong? That's the first question.
so we check it against null.
I don't really understand your question, Friedemann. The reason we focus on block sizes is because we don't want confusion in the code. And if we only use payload sizes, we're going to have to add the overhead, so the size of the metadata all the time. And it's going to result into overloaded code. Whereas if you directly use block sizes, well, we don't have anything more to write. We just compare block sizes and it works. So it leads to lighter, easier to read code. Yeah, okay. So as usual, there is an empty line around blocks inside the code. That's just, that's me, coding style.
Around if statements, or how do you mean?
I mean, this is not valid coding style for this project.
Okay.
That's all, nothing
Okay.
more. So now you're here, you have a block, you know that this block is not null. Okay.
Uh,
And same thing here. Yeah, except, wait. You left something here. Oops. Okay, fine. Git will show
uh,
you if you leave
against
empty white spaces anyway.
yeah. Um, so we have a free block, and then we need to allocate it, I suppose.
Okay, I guess it's right. We'll see.
But that's in this function. So,
Is it?
or would you write another
Well, yes, we have. It's a
primitive for
block,
that?
so we're going to use block methods. Yes. So it's not really allocate, because what you're really doing is that you set the allocated flag to true. So it's really set allocated. And wait, no, no, no. You're passing the address of block, whereas here you have a pointer.
Oh, whoops.
Okay, so your block is now allocated. Okay, that's good.
And then um, we haven't checked against. Um, we haven't actually against the possibility of it being um, a large enough block, but
Yep.
too large, and that you have to allocate the second block.
Yeah,
Um,
I would do that too now. Yeah.
um, so in that case, what would you just return the entire block size of
So
what is
in
available?
in the case where it can't be broken down into two, well, first you
Uh,
should write the check actually, and then we ask the question.
um, size. Uh, okay, so here you just get back
Yeah.
the
By the
size of
way,
the
I
block.
just noticed something. Sorry, sorry. You find a free block, but you don't give it the size you want here.
Oops. um, yeah, so this is just the entire size of the block that is available, right?
Hmm.
Or
Well, this is the size of the block we want. The minimum size of a block. Like the block could be larger. It may be larger if
oh,
it
this
if it
one.
cannot be
Yeah.
broken down, but this is the requested size converted to a block size. That's all. The point of this line is to forget about payload sizes. From now on, size means block size, so there is no confusion.
Uh, but then you'd have to check before you allocate the block, or is that no? Because you know that it fits
Yeah,
at least, and then after that you check
exactly.
if there's enough space
And
left.
so you see why I talked about this earlier. Another way to do it was to check now whether the block fits or not, and if it doesn't, we break it into two, and only then we set the allocated flag on the first. We could do that, but then you have more conditions to check. Your path becomes more complicated. Whereas if you do it that way, if you always remove first and set allocated first, and then you check the size, the code becomes smaller. And the only reason I can say that is because I already see what the code is going to look like. So, but you could try both and compare and see for yourself.
Um, so how do we check what kind of a type would the block be? Memory block?
I don't understand the question.
'Cause we need to see if the size
Yeah.
or what the actual size of this block is.
Hmm.
So,
So you
uh,
have you have look you have methods for that.
oh, block size. Whoops.
Accessors. Yes, that's where the bugs are, right?
Yeah.
So always talk so that we know what's in your mind at the same time.
Okay,
And
so
remember, we have written this. Oh, ah,
yeah, it's in the other one. It's kind of annoying that it
saving,
doesn't update.
reloading. Yeah, it's super annoying. My God. Anyway, yeah, we have this. We don't know the value yet. We don't care about the value. We know what it means. So you can use that here.
Exactly. Plus the size of this.
Plus the size. Why?
Or
Well,
uh oh no, because if we've
well,
allocated
yes.
already.
No, I mean you're right. Plus the size because this is the size of the block we want. Basically, this is the full size, and we want to break it into two blocks. One of this size and the other which has at least this size. So yeah, it's a little complicated, but I'm going to let you, you know, do the work. Okay, so this is C, and this is C with my coding
Oh,
rules, where all operators, when there is even a slight chance of like confusing operator precedence, we force it with parentheses. Because if you write it that way, sometimes the compiler is going to emit warnings because it's confusing. Compilers do that more and more. Sometimes it's annoying. For example, modern compilers um, emit warnings when you have fall throughs in switch case. For example, if you have a switch case and you have two or three cases, and the first two fall through to the third because there is no break, the compiler is gonna emit a warning. And if you if you have flags that tell your compiler to transform warnings into errors, your program is going to fail building despite being correct. So yeah, but it's a mistake that often occurs to forget about breaks in switches. So there's a reason.
So you,
No, I was just saying that I want to force operator precedence
yeah.
to avoid such warnings. That's all.
Um, okay, so
So let's
now,
let's check let's check whether it's actually true. So mem block size. This is the complete size of the block we found. Okay. If it's strictly greater than size, which is the requested size, plus the minimum size of a block, which would be the size of a second block, then okay. So no, it's not correct.
because it can also be equal.
Yeah. And I suspect that you
Um,
were thinking about that.
and no, I kind of skipped over that actually.
Ah,
I was thinking about how do you do you then have to find another free block? Well, you know that it's free.
no, you
Um,
break it into two.
so you allocate another piece, but
Well, you need to create two blocks. You need to split it. Split would be a good word actually. Block split.
you've oh right. Um,
So you pass it the block
no,
because that's what you want to split, and then the whole yeah. So one of the big, um, the difficult tasks of a good software designer is creating good interfaces. And good interfaces here means good functions with a good signature. So how are you going to do that? How are you going to split a block into two, return that to the caller in a way that both tells the caller whether it failed or not, and in case of success, returns it the second block? And in a way that is non-ambiguous about which block is the first and which is the second, also.
makes so you have uh two parameters or one input block essentially and one output. Or is that not what you're saying? Do you want to leave the return type for error
No, no,
checking?
I'm saying
Or
find the most elegant way to write to call this function, not to write this function, to call this function.
yeah, so you're wondering about parameters, right?
I don't know.
Of this function.
I don't know. Honestly, I don't know. I'm waiting to see. But I can already feel that it's going to be, yeah, it's a
Because this is your input.
tricky case of interface design.
Uh, I'm not actually quite sure.
Try.
You don't have. Um,
So what does this function do?
well, you give it the block that
Okay,
that has the entire area.
well, a block,
So this with this size.
a block. You give it a block.
Yeah,
Okay,
yeah.
and what does it do?
Um, what should return two?
Okay,
Is it two? I'm still a little bit confused about this set allocation because you're
well,
um
this only sets this bool to true. That's all. And yeah, we didn't remove it from the free list, by the way. We should do that before forgetting. So we have a flist add method. So just yes, flist remove or delete, whatever, both work. I like remove too.
Um, and remove a block.
Yeah. Okay. So it's allocated and it's out of the free list. That's exactly what we want, isn't it?
So yes, so we have
Yeah. Basically, we're in
this.
this case now. Yes, we have one big block allocated. Yeah.
Mhm.
And now we know that this block can be broken into two. So split is the word we're using here. And so yeah, you have one block. You want two blocks, and you want them split at a specific boundary. So this is given by the size. Okay.
Um, um,
What are you thinking?
you, well, this would be the size I think that you give it. Um, oh wait, no, because this is the memory block size.
This is the size we want.
Yes,
So this is going to be the
but
size of the first block.
yeah,
Okay. Now, what I don't understand is why you have block twice here. What's
yeah.
the
I'm not
first?
quite
What's the
sure.
second?
Well, it's 1 and 2, but I'm not sure what to call it because we have our first block,
Well,
which we can
you could
keep.
call it. But let's find good names. Uh, this one could remain block, right? It's the first block. Okay, so it already points to the beginning of the block, so it's going to point to the first block. Now, block two, we could call it that, but
Split block.
um, this block gets allocated, whereas the new block here is going to be freed. So we could call it free block, or honestly, I
Could
don't
be
think it
split
matters
block.
much here. I think people would understand block two as well. And free block might be misleading because currently the block, uh, the block, like
They're both
when we
split.
split a block, the most intuitive thing to expect, the least surprising thing to expect, is that both blocks have the same properties. So if the first is allocated, we expect the second to be allocated too, right?
Yeah. So we after that you allocate it, right?
So naming it free block and then set free may be confusing. Whereas block two is fine. I don't have a problem with block two. Can the operation fail?
Uh, don't. Because well, you know that it's
Hmm.
the size is right
Yeah.
or large enough at least.
So can it fail?
I don't think so.
I don't think it fails either. And immediately I'm thinking of a way to refactor this. So this here, don't forget, this here is a macroscopic function, right? It's an entry point, it's high level. We try to make it as abstract as possible. And checking sizes this way in such functions is, like, if you can avoid it, it's best. Because this should really be the logic, the high level logic, and then all the details should be hidden into other small local functions. So one way to rewrite this would be this. Uh, let's comment it out for now to keep it. We could call it like this.
Oh, I thought that you wanted I
It's
thought
not.
you wanted error types or error return types.
Well, it
Return
depends.
value.
Let's check the coding style again. So, functions, common call protocols. Okay, so type get value is, well, an accessor. That's the simple thing. Do something, function that cannot fail. Okay, then you have those two. So you have lookup, which basically returns a pointer, but it's not necessarily lookup. It it returns an object. That's what really matters. And if like if there is a single error that may be possible. So here basically the error is that we can't have a second block because the block we have is too small for that, right? It's the only error we can have.
Yeah.
That's the only condition we tested. In that case, you can return null because null, which is a single value, can encode a single error. But if you need more errors, that's when you're going to use that kind of protocol,
Okay,
and
that's
then
why
you're
you.
going to pass the pointer as a point-to-pointer argument.
Yeah. Okay.
So same thing here, create, you see, functions the same as this, return null if an error occurs, which may only be error no mem, see? There is a single error, so you know what this error is. But if, yeah, if, I think it's written here, if there is a single possible error code, yeah, exactly. So, if your creation, for example, could fail because of a lack of memory or an invalid argument, then you return an error code.
Okay.
So here, because we have only a single possible error, we don't need an error code, and it makes the code simpler. We have one less variable to combine. Okay, so now we have block 2, we set it free, and then we want to add it to the free list again.
Oh, right. Uh, I think is. Yeah.
Okay, so one
What?
thing we could immediately think of uh, is the state of the block when we add and remove it to a free list, because this will allow us to add assertions, and assertions at such points will make the code more reliable. For example, if when you remove a block from the free list, it has to be free first, and so you can make an assertion, you can add an assertion in that place, you know that removing a block will necessarily make it allocated. So, for example, we could uh, we could call that from the remove function here,
Mm-hmm.
and same for here. So I guess we're gonna do it this way.
Yeah.
Okay. So what else do we need to do?
Um, when you uh, when you remove it though, the same boundary tag which has the allocated bool is also in the footer tag. Um,
We don't care. We're manipulating blocks here.
but here you said that it's allocate or
Yeah,
uh,
that's the block. So that function is going to do to set the flags both for the header and the footer. That's the difference between the header boundary tag and the block.
okay. And so what you do here is you then set the footer of this block again. If the block is going to be added, since there is one,
Yeah.
uh, it um, it says the allocation boundary tags for this, and you don't have a trailing allocated boundary tag.
I don't understand.
Um, here you set both allocated
Yeah.
tags, right? If you then don't make sure that in the second block you remove that allocation from the footer.
Well, actually, no. Why the footer? I don't understand. We split them here. We have two blocks here. Both have their own boundary tags.
Uh, and the
Actually,
second one is just
I'm wondering if we really need, do we really need footer boundary tags now that I think about it?
well, they don't use them in the example
Well,
necessarily,
here,
or in that.
what we call the footer boundary tag could also be the header boundary tag of the next block. So maybe we don't need the footer boundary tag, but that's okay. See, I don't care about those problems here because this is all logic. This is all high level. I remove a block from a free list, I split it, and if I have a second block, I add that second block to the free list.
Yeah.
I
Okay.
don't care about
Okay.
how it's implemented. These
Yeah.
details will be handled in those functions that don't exist yet, and
Okay.
we'll think about them when we work on those functions. So here in that big logic stuff, is there anything missing?
Um,
Well, obviously the end, because we don't want to return null, but other than that,
I don't think so.
I think it looks good too. We might see errors later because we're streaming and sometimes we just forget things completely. But I don't think I think the bulk of it is there. So yeah, let's fix that. And so let's add the variables and then let's write the functions.
Um, oh, I blocked two.
Okay.
There we go.
Okay, that looks fine to me.
Then we go ahead and write these.
Mhm.
Actually,
So just one word about the order of functions, as you can see here, although here it's very small. Um, This is what we call a static global function. Not static in the sense that it's private. This keyword here should really be private in C. Static in the sense that it has global storage, that it's not linked to an instantiated object. See, this one needs an object. This one
mm-hmm.
doesn't. This one is global, static. So sta that one is static too, by the way. So static functions are usually written, well, they're usually on their own, not necessarily, but the point here is grouping functions around the same uh, finer grade functionality. So for example, these are global functions that would be here. They're basically unrelated, so we can put them anywhere, but at the end is usually good because of for declaration. You need to declare what you're going to use before using it. So putting those functions at the end is usually a good thing. That one could be at the very beginning too, that's okay. What's important is that, for example, the methods are grouped together. So for example, these are the freelist methods. These are the block methods, okay? And then we have the footer boundary tag methods, and then the header boundary tag methods, and then the boundary tag methods. Um, and I don't want to see, like, if it's possible, group all those methods together. But sometimes it's not possible because you have dependencies. And my personal rule is that it's better to have a weird ordering of declaration rather than having duplication caused by forward declaration. So basically, if you have to declare a prototype of a static function internally, because you can't maintain order otherwise. My personal answer to that is that it's better to break order and avoid writing that prototype, that additional prototype. It's better to have just those functions declared and defined at a single location and then use them rather than having prototypes declared and then having the functions. So as few prototypes as possible. It takes precedence over keeping the order of methods and functions.
Okay.
But again, that's just coding rules.
Also, this would be a free list find block, maybe, since we
Yeah,
have
yeah,
it to
actually,
free.
yeah. Nice catch.
Okay, so this one is going to be at the just at the start.
So we could wait. We
Or
could actually find block. We know it's a block because that's the only thing free list contain. But find free is what is
ah.
interesting. Well, actually, even find because it's always free.
Mm-hmm.
So yeah, add, remove, find. These are the three very common operations of any container. So we have good names here.
Uh, so you said that this is a function that you add at the start,
Well,
or
it really
I mean it doesn't.
it doesn't matter, but yeah, here personally I would put it as close to memmalloc as possible because that's where it's used. So there is a direct relation between them, but sometimes you'll see that it makes sense to have them at other locations in the code. It doesn't really matter as long as functions which like methods which concern the same object, the same types, are grouped together.
Uh, so this is your payload size, uh, and you add the size of the boundary tags,
Mhm.
right?
So just one thing, because um, I think we're overthinking this, and I really think footer boundary tags are actually not very useful. So before you write that, because otherwise we're going to have to change a lot of code, I'm going to remove them immediately. Whoa, what? Oh, okay. So let's reload. Um, is there any reason? I don't see any reason really. And even the header boundary tag now don't make sense. The only thing we want. Oh shit. Okay. The only thing we want actually is this. That's interesting. And that's it. And those things just go away. And because we wrote a lot of small functions, it's going to be very easy to refactor quickly. So let's see. All those things go away. Yeah. Okay. So this is only b tag, okay. Allocated, same. Um,
You missed one.
so I missed one. Yeah, probably. Yeah, you're right.
Oh,
So now this one is the more problematic one. It would be the next, right? Get next b tag. That would make sense.
mm,
And so yeah, b tag. That would be so we have the block cast into a pointer to characters plus the size of the block. Okay, and that's a boundary tag. Yes. Um, and so we don't even need to do that. See, simplified.
well, yeah, so
We well, we return the one of the boundary tag of the next block.
oh, right.
See?
Okay. Yeah.
Because now that I look at it, the problem with that image is that we only see one block. You have to see one block after, one block before, and then you see that there is the footer boundary tag and the header boundary tag and the footer boundary tag and the header boundary tag. And this duplication is useless. I don't see why we need that. So this image is actually misleading because of that.
It should be cut off here, you'd think.
Yeah. But
What
it's
would
better
be the
if
reason?
it would be better if we actually saw two or even three blocks.
Oh yeah, yeah.
Okay, so we have the boundary tag, it's correctly cast. Okay. So now we don't need this. Okay, the boundary tag has a header. Um, okay, and normally that's all we need. If we miss something, the compiler is going to tell us anyway because we were careful about the structures. Note that there is a hole here, right? This is
Hmm.
4 or 8 on 64 bits, but this is a 32-bit system, so we know that it's 4 bytes. This is 1, usually, but you can't rely on it being 1. And then this, because it has to be aligned on the size of this, which is also 2 pointers, means that there are 3 bytes of padding between the two. And this is guaranteed by the C specification. Okay, what else should be done here? This looks good. Okay, so this function is not going to be used right now. Um, so the compiler is going to complain that it's not used, but that's okay. Okay, well, you can go ahead. So let's have the types. Let's actually save it. Let's reload. Let's edit, and there you go.
Uh, so how would you go about getting the size, or what is the size of the boundary tags again?
Well, well, what? How would you write it?
Uh,
So
have
there is an
some kind of
operator in
macro for it,
C.
but
There is an operator in C, which is very, very important. That operator, along with a couple of other rules, is like the the foundation of reliable code in C. And this operator is size off exactly. And I'm going to repeat it every time I have an opportunity. Um, Use size off on variables as much as possible, not on types, because your variable might change type without the associated size of changing automatically their type inside. Whereas when you if you use size of on variables, when the type of a variable changes, well, the return of the size of operator is going to change automatically without having to take care of anything.
so the size of the memory boundary tag. Or,
Yes, but is there a way we could avoid using the type? I don't think we could avoid that right now. Um, yeah, I don't think we could avoid that. So here you probably have to use size of on types, not variables. That's not
oh,
what you're doing
sorry,
right now.
sorry.
Yeah. So that's the boundary tag, but that's not enough.
Okay.
You
How,
have
how so?
to you have to return the minimum size of a block.
Uh,
We said that this is where we wanted to handle that problem because this function is about block sizes. So let's handle block
oh,
size problems
wait.
there. No, 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 no. No, no, no. The user here could pass 1. And here we want to convert 1 or 2 or 3 into a block size. And we want that block size to be valid. So we really want here to check that the size we return is at least the minimum block size. So hello, FerryMacG. Yeah. It really doesn't matter whether you use struct or type def. What I'm saying is that you should use size of on variables, not types, whether they're defined with type def or not. Yeah, it's the contrary. Yeah,
Oh, I
it's less than the block min size.
yeah. There we go.
So the reason is when you change the type of a variable, sizeOf is automatically going to return the new size of the type. Whereas if you use sizeOf on a type, if you change the type of your variable, sizeOf is not going to change automatically. You're going to do that yourself manually. And you want to avoid manual work. It's slow and it's error prone. So here we have no variable. That's why we're using sizeOf on a type. But as often as you can, as much as you can, use sizeOf on variables, not types. And new line. So yeah, that's actually good. And here we have the boundary tag, but is there anything else? We don't need the headers because the block, well, we know that the size is at least. Wait, no, that's not good. No. You're checking a payload size against a block size. So this function is about converting to block size. So this is the one location in the entire code where you're going to have payload size and block size, right?
Mm-hmm.
You have to care about that. You have to first convert into a block size and then make sure that the size you return is at least the minimum block size.
Oh, right. So like this.
Mm-hmm.
Maybe.
And to make it, we don't like having multiple return points if we can avoid it. So
Yeah.
also, it's not all. Remember alignment constraints?
Yes.
We want the size to be aligned on specific values. So I think the way it's specified here is by saying that it's suitably aligned for any built-in type. So basically, char, short, int, long, and long long. And what it really says is basically that it should be aligned to the machine word size. And here we are on a 32 bits processors, which means that we have 32 bits words, so basically 4 bytes. So before even converting here into a block size, we need to transform that size, that payload size, into a suitable payload size. So here, do we have alignment here?
Mm-hmm.
Yeah, we could have a macro for that. Let's have a. Well, do we really need a macro? It's better that we have a macro because then we can comment it here. So mem align, and let's write 4 or size of int, for example. But yeah, it's good like this. Okay, and then here. So you want me to do this or not? Oh, this
Yes.
is
Please. Yep.
oh shit! What did I do? I dropped the changes. Okay, look, this is more than
I'll.
annoying. So sorry. I think we should stop doing that, and let's just use Vim and just ask me
Sure.
when you need stuff because I can't I can't work like
Too much of
this.
a hassle. Yeah.
So well, yeah. Hello for
Uh,
MacG. Wait, yeah, I was answering chat. So let's see. So we do have memoline. Oh yeah, the keyboard too is a little annoying when we share it, but that's okay. So yeah, I'll write it here. Whoa, what's happening? Oh, that's right. Okay. So first, let's convert the size. So size equal, we want to align it. And so word sizes are powers of 2. And it happens that in my macros, I have power of 2 conversion macros here. So what we want basically be this, round. Oh, yeah, okay, it uses the mouse. So size is power of 2 round of size. You can do it yourself. Like you can write down those operations yourself and see that they work. Um, I've done them a very long time ago. Like I think this code is 15 years old or something. Maybe there are probably other ways to write it without using minus, but minus is very convenient when you have a two's complement. When you have two's complement representation, so that's what I decided to use, despite the fact that it's probably confusing, but it's very efficient. So I also need the alignment. So here the alignment would be mem align. So for example now, because mem align is 4, if we pass 1, this is going to be 4. If we pass 2 or 3, this is going to be 4 too. If we pass 4, obviously it's going to remain 4. If we pass 5, it's going to be 8, etc. You see what I'm doing?
Yep.
Where I'm going with
Yep.
this? Okay. So that's the first thing. We could also assert that the size is not 0, but we don't really need to do that because 0 would work actually. Bye Zirpai. Thanks for stopping by and moderating the channel.
Well,
Um,
it won't be 0 because then
yes,
mem
but
alloc
yes, but the point of having small functions like this is to make problems local, to avoid relying on things that are remote and
Ah,
might change without notification. So basically, don't make strong assumptions like this, because someday you might realize, oh, we have a good reason to remove that check, and if your code is fragile and relies on that check, it's going to break. And maybe it would
mm,
break silently with memory corruption, and you wouldn't know, and it would cost a lot to people who would be very angry and would, I don't know, start a trial against you, in the worst of cases.
yeah,
I don't know if a rocket explodes because of that, because it
yeah, yeah,
happens. So you want to make code really rock solid and robust. And to do that, you want to minimize your assumptions. So here we want to make the code work, even if it's 0, ideally, without additional effort. So here, like you did, size of struct boundary tag. Okay, so the size of a boundary tag, really. And then we check, wait. Okay, it does things correctly. Or maybe not, shit. Okay, we won't have tabs. We could change that, but I'm lazy. If you want, I still have to set to upload
for
my
next.
my dot files somewhere on the Git repository. I didn't do that. Sorry, guys.
Do that for
Uh,
next time then.
so
Use bin
uh,
from now on.
if the size is less than the minimum size of a block, yeah, that's really annoying. That's going to be annoying too. Look, I'm going to copy I'm going to copy my vmrc right away because otherwise it's going to be even more annoying. Okay, this should be good. I don't think we rely on much in there. Okay. Much better. Okay. So that's basically it, I think. If you see mistakes, don't hesitate to tell us. But I guess we'll see when we run the code. So that's one function, and it's complete. You can move on to the next. Or I think there is no mouse here.
Release.
Yeah, there is no mouse.
Whoops.
So
Okay. Page up. Does
that's
that work? Or
what?
that's page up. How
Yeah, that's
far
page up,
did
but
I
that's
go?
not what you want. So I'm going to let you actually use gedit for your part if you want, but yeah, I mean, you won't be able to have your structures nicely packed on one part of the screen and the rest. You won't be able to split your screen nicely. But use gedit if you want to, because I don't want to you know to be too much in your way.
Uh,
And I understand that Veeam can be
Things like copying and stuff with
yeah,
single
hostile
characters.
for new
Yeah.
users. One thing we didn't do though, the function is not really complete because we don't have the value of the minimum block size. So that's one thing we should do right now.
Oh, right. Uh, this one. Um,
So it's
and
it's very visual, right? It's basically this plus this, and that's it.
and since those are aligned by 4, you can assume it's 12, or am I wrong in that assumption?
So that's a good question. Um, they are aligned by 4, so we it's going to be 12, I think, yes. But we don't want to write 12. We want to write size off, okay? Because if you add things in your structures, you want your minimum block size to change automatically without thinking about it, without having to remember to change it.
So again, the size of
So yeah, it's
this
the
one.
size of a boundary tag plus the size of something else.
Um,
So that's why I
that's
wanted
the
to
header.
show you this, yes. Thinking about memory visually is a great way to quickly understand what you're doing.
Okay.
Wait. Is that all? Are we missing something?
In the macro.
So it's the boundary tag plus the free list header, basically. So we don't have footer boundary tags anymore, but we still have one constraint, which is that the minimum block size must be aligned on 4 bytes. Now here we know that these structures are aligned because we know that they have, we know that because of the alignment of their members. But again, you're making an assumption here that these structures will always be aligned. So either you could let it that way because it's very unlikely to change. But for example, imagine that we want an alignment of 8 or even 16. Imagine that even on a 32-bit system, you have code that, I don't know, uses SSE instructions. And SSE instructions require 16 bytes aligned words. Well, really values. They're not even words anymore. Um, so in this case, for example, we might want to change the alignment to 8 or 16, and we would still want this to work. So basically, what we could write here is something like this.
And add
We'd
the
use P2
P2
round
here.
again, yeah. So we'd have the size here, and we could yeah, this goes too far on the right, so let's break it. Okay. And then it would be a line to memo line, right? And then whatever you have is going to work, right? You can change the alignment, you can change the structures, it's going to work
Yep.
at no cost, really, because these kind of macros,
Compile time.
yeah, they are computed at compile time, so they don't cost anything.
Which is really nice. Yep. Uh, Crap.
It is static, but the return type is not good.
because it returns a block.
Yeah, no, the pointer is at the end. It's like when you declare a pointer, it's always type, some stars, name. No name, it's not a variable here. It's just a, yeah. So it's part of a type, and
Oh.
it's like this.
Oh, right. Okay. Okay. Sorry. Uh, so here we want that uh,
Yeah.
iteration.
So we're going to find that in the list module. For each entry, there are two variants here. One operates on nodes, and another operates on entry, which is a little more convenient.
Uh,
It's not list.
so
It's definitely not list.
oh, right. Oh, this is
Well, it's very easy actually. Look, that's what you use here.
oh, for that. So what exactly is the entry? What is the
It's your iterator.
number?
So it's just an entry, a pointer that is going to take the values of all entries in your list sequentially. And the member is the name of the node member you used when declaring your, well, when defining your entry, your structure. So here you have to provide memory for that. You have to provide memory for that pointer. Yes. Mm-hmm.
Uh, and the member again? Well,
Well, the member is going to be, so that's, yeah, that's a little complicated. It's actually going to be in the B tag. It's going to be this. So I'm not sure we can
we have.
actually. I don't think we can actually work directly with blocks here. And this actually is not good. Not good at all. I'm going to change that immediately. Just one moment, because we might probably need that after. Okay, and then we should have B tag header. Do we already have it? I don't think we have.
It would have been in the HB tag.
Indie?
HB tag, the header B tag.
Oh, yeah, maybe I removed it. Whatever. So struct memf header. Okay. Now here I don't think we can directly. Where is it? I don't think we can directly use uh, the member of a block, because it's not the member of a block. It's actually the member of a boundary tag here. So because we simplified by removing the footer and the header boundary tags, we could actually consider that a block is a boundary tag. We could merge the two, right? But
Mhm.
I must say that, yeah, I like this distinction. I like that it separates the two. The block is the whole, and boundary tag is just the beginning. So then, what we could do here is that. So yeah, we have a header, Um, yes, that's quite annoying. Actually, what we have in the list is not blocks, it's headers,
There. Yeah.
right? Like
Hmm.
this. See? So what we do is that we go over our headers, and for each header we get back the block, right? And so here in header, the name is node, which is the name I usually use and recommend for these kind of things. And it's not ending, like it's really a for loop. So that's how you should write it down. So now you need to get the block from that header. Do you see how you can do that?
Um, you check. Oh, you have to offset, right? Well, you
Hmm.
want to have find the boundary tags which you will. Oh, wait. Um,
But do you see how to
yeah,
write it in C? Because I mean, it's quite
not
obvious
quite sure.
that
That's
you
quite new.
basically have this address and you subtract the size of the boundary tag. It's basically it. But do you know how to write it cleanly in C?
I don't think so. No, I've
Okay.
not never used anything like this
Yeah,
before.
it's actually not. You'll see, it's not like, even if it's not a variable size array over. I don't remember the name exactly. Don't worry, it's the same. It's exactly the same way to write it. So we want a block. Okay. So what we do, for example, is block is mem f header get block, for example, and we pass a header. So we'll do that later because yeah, it's excluded. It's out of the problem. Okay. Consider it solved, and we'll go back to it later. So you have a block. What do you do with that block?
Um,
You know it's free,
after okay. Um,
and you know it can't fail. If you have a header, you must have a block.
see. Is it here where you uh check it against the size? I
Mhm.
forget what we're doing down here.
We're looking for a block that has at least the size we want.
The block size you want. Okay. Uh, so if the block size, oh, that's the if block size is less than return null. If greater or equal.
Well, it's something like this. Yes. I'll let you write the code, and we'll see after.
Um, if the size is less than,
Less than?
right?
Well, I'll let you
If the
finish, and
size,
we'll see. So the size here is the requested block size. Okay, we only work in block sizes now. We don't care about the payload size. It's a block size. So what? Well, continue. We'll see.
isn't it sort of, no, we're checking against this as well, right?
Well, the size is at least that because it has been done before. That's a requirement. No, 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 no. That's not it. You have a block here. So first, empty line. You have a block. You want to make. Well, you want to see if that block can hold that size. That's all.
So if the size of the block,
Hmm.
um, Size of block, does that work?
No, 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 no,
I don't
no.
think so.
Size of is a compiler operator that returns the size of a type or a variable. Here, it's the size of the complete block we want. It's this thing we want.
Oh, right.
And this is why I like to have blocks and boundary tags separated, even though the block is just a boundary tag in the structure. Because when you talk about blocks, you talk about the whole block. And when you talk about the boundary tag, you only talk about the header. So every time you write less than or greater than, ask about or equal. Are you
Because
sure?
it can be equal.
Are you sure?
Well, if it's the same, if it's the same size as you're requesting, then
Yeah, it's a perfect fit, so yes.
yeah. Um, so then you return block.
Okay.
And otherwise it would be null, right?
Otherwise,
If it can't find a block, if it can't see that
if it can't
it's
find the
greater or
block,
equal,
yeah.
then will this remain null?
Yeah, but I mean, careful about words because the way you said it is otherwise. So otherwise basically translates to else here, which is not what we want to
Mm-hmm.
write because then you would only check one block. What you
Yeah.
want to write is something here after you have uh, performed the search. No, you left something here.
Sorry. What?
No, I removed it. You left spaces,
Oh, whoops. Um,
and I have a coding style OCD. So is that really necessary? And actually, is
if
that
it just
true?
return
Because
block.
careful, careful, your block here is uninitialized. Your list could be empty, in which case your block would remain uninitialized here. And actually, if you enter that and you don't find a block, your block is not going to be null, it's going to be the last one you checked. So that's three reasons not to write this. Actually, do you actually need to write anything?
I don't think so. Can't you just? Oh wait. Um, so the block is the last block that it iterates over if it's um
You're making it much more complicated than it is. You said it yourself. If you didn't find a block, then
oh
see, and that's that form here. You iterate over your container, and you don't find anything. You return something that tells you didn't find.
yeah.
Is this form is really very classic. It's really what you should look, what you should aim to write. Like every time you have a simple search in a container, um, you may not have that kind of uh, of terminology. For example, you'll have an iterator, so it will be a for each maybe, but not necessarily a list. It might be a tree, it might be an array, whatever. But it's usually how it's done. You look for a thing in a loop, or with functional programming with recursive functions, for example, or a map or something. And then if you reach some point, you return something that says I didn't find.
Yeah. And had to remove
So where are we
which
now?
Adding the free list
Okay,
removal.
so I have just one thing I want to do right now, like really right
Okay.
now. When we initialize here, when we set up, we use flist add. Okay, so add to the free list flist init here.
Oh yeah, the
Um,
allocation
flist init.
or
Oh, it's here.
allocated
Okay, there is
tool.
a list init on the header. Okay, okay. Um, block init then. Block init calls boundary tag init, which sets allocated to false. That bothers me. Let's make it allocated by default, because then, if it's allocated by default, what we can do is that when we add a block to the free list, so here, we can assert, yes, that the block is actually allocated. Okay, we add allocated blocks to the free list, and this means that here we can turn them into free blocks. And this means that we restrict where a block can become allocated or free. And we couple that with the insertion or the removal to or from the free list, right? So we we create strong coupling between the allocation flag and the presence in the free list by doing that. I actually said free. And that's it. So yeah, here, for example, I can now remove this because it's going to be done by this function, and I can remove this because, as I just did, this function does it.
Hmm.
And that's the point. Less code and less risks of mistakes, because now setting or clearing the allocation flag is done when adding or removing to or from the free list only.
Um, do you normally sort by function or on or alphabetically? So add the remove
I don't
after.
care. I don't care. As long as they're grouped, I really don't care. Like create, destroy, destroy, create, add, remove, add, I don't care. Like I said last time, you see your initialization function is at the bottom, and depending on how your personal taste of ordering is, it could be at the top. It's usually not in the middle because of that reason, because you initialize first and you add other functions after. That's really, it's not very important as long as it's grouped.
Okay.
So when you remove, you assert that it's not allocated. Okay, so yes, you expect the block to be free, and then yeah, it becomes allocated. Makes sense. Well, you have to write the rest of the code, obviously.
Oh wait.
Hmm? What did you just? Oh, okay.
There we go. Uh,
No, C doesn't have something like that for ImageG. Absolutely not.
list insert tails.
And this is, sorry, Metal Snake. This is why I insist on this form here. That's really the standard way to implement something like find if, and many people don't have that kind of automatism to to separate those, like to recreate what these higher level languages provide by default because of years of good practice, because they know that that's how things work basically. In C, you have to do that yourself, and because people are not accustomed to that, they don't have the reflex to write that kind of find, add, remove functions. Well, some do obviously, but many people don't, and it leads to, that's one of the reasons why you end up with spaghetti code many times, and global variables everywhere and big functions. So that's why I want to insist on these small functions that find. It's very standard and it's very close to what you have in other languages for a cost that is not that much. It's basically a for loop, right, and a condition check. But it has to become a habit. It has to be automatic. checklist remove. There is something special about list remove. It doesn't need the
Uh,
list.
Oh, okay.
And the reason is because uh, the prev and next members might directly point to the list head.
Okay. Which might be
I mean,
no.
here,
Is it?
prev and next might be the list head, in which case the next and prev pointers, which are actually the first and last pointers of the list head, are already updated, which means we don't need the list head here, just the node.
Oh, okay. So this would be the remove function.
Hmm. Yeah, so you see here, you're actually not using the list. So
Oh,
the compiler is going to complain that you're not using an argument. So what we do in this case is that we write this. This is the standard way to tell the compiler, well, to create side effect, basically. The side
what is
effect
the?
being that you
Sorry.
read a variable. The compiler is going to see that you actually don't read it, so it's not going to generate instructions. Well, actually, it's going to see that you don't use it. So if you don't use it, you don't need its value, so you don't need to load it from memory. So this line costs nothing, but semantically it tells the compiler that you are accessing the variable.
What is the reason for keeping it in there and not just removing it?
We could remove it. We do it for purely for form reasons. Um, to keep it object oriented, so that we have the object as the first argument, and so here it doesn't really matter because it's internal. But imagine that you have a public interface, and one day you change the implementation, and suddenly you do need the list. In those cases, you don't want to change the interface
Okay.
because it became public and programs are using it, and if you change the interface, you're going to break everything.
Okay. Um, have a look. Then block split.
Oh, that one is going to be fun.
And returns a block, takes a block and a size.
So what I usually recommend is to avoid writing comments, because usually you can make your code be meaningful enough that you don't need the comments. And sometimes, obviously, it's not enough. The code itself can hardly convey all the details that you need to know. This function is probably one of such cases. But because you're going to comment just this function and almost none other, it helps the reader know where the tricky stuff is by just looking at the code. Not even reading it, just seeing that there is a comment here tells the reader, be careful about that part of the code.
So you keep this
No,
existing
this
comment
one
in
this
there.
one would be moved to split, obviously, but the block split function, like explain what the arguments are, what the return value is, what the failure cases might be, and maybe why it was
Ah,
done this
okay.
way to avoid useless refactoring, things like that. How do you feel about common blocks above function? Well, you can see on the right, I use them. But I guess you want more details about that. Um, so usually I will write comments above all prototypes and obviously static inline functions in public headers. So um, well, usually in headers, and usually I try to make all my headers somewhat public, you know, because I consider that the programming unit is really the file, and a file matches a module, and a module matches a single functionality, you know, a macroscopic functionality. So my basic development unit is the file, the module, the functionality, etc. So the header that matches this module is normally public. And so yeah, I try to comment all the public functions, but internally I use as the least possible comments. And yeah, sorry, Metal Snake, I'd like to give you an example of that, like a really in-depth example. Let's see. The timer might be a good, or the turnstile. The turnstile is a good example, yes. The turnstile is probably the most complicated code in the kernel. So this is X15, not X1. Turnstiles are priority propagation sleep queues. So basically, there are sleep queues with priority inheritance for real-time systems, and priority inheritance works in chains of threads and mutexes. So it's quite complicated, and it works on a multiprocessor system. So you can imagine that it's tricky. So here, this is the public header. I tell the users what they need to know. They need to know how they use it, what for, what it is for, and then they need to know the interface. So they need to know about thread data. They need to know these things. Here it's so obvious that I didn't even uh, spent wasted time writing comments. Um, but here we go into the details. So create destroy is pretty straightforward. Acquire release basically too. It's basically locking and it disables preemption. Landing and returning, that's not intuitive. We need to define what landing and returning is. So there is more text here. Empty, that's okay, except, yeah, has no waiters. That's really the meaning. And we give the precision that it must be acquired before we can call this function. And here we have the much more complicated stuff with a lot more comments. And this is the implementation. So here I tell what people who review the code need to know. So I tell about locking orders. I tell about references. So I give them a reference to the original description of the implementation. I talk about the difference between that and what the code actually does. I document the data. Okay, but the rest of it is almost not documented. Like there is one function which is a little documented, which is this one. It's the heart of the algorithm. Okay, it's literally the propagation loop. So yeah, here this is complicated. There are things about locking states and reference counters. So yeah, but after that, it's like almost nothing is commented because it doesn't need to be. Like this is acquired, it was already defined. Release, same. Push free, well, we push a free turnstile into the free list of a turnstile. This is described in the comments about the structure, so commenting the data but not the code. Pop free, push free, symmetric. Land, return, already described. Empty, update owner. That one is a little more complicated. Again, it's described at the top of the file when commenting the structure. Wait common, well, it's common code for waiting. And the wait and timed wait functions have been described already. Same for signal, own, disown. And it's only 150 lines of code. So yeah, what really matters is describing your data and describing your public interface. Because this tells someone that doesn't really know about your code how to use it, and this one tells someone who wants to know more about your code what it's about. And it's about the data, not the code itself. When you know the data, the code normally, you can derive the code easily. And this is something that you can see already in what Metal Snake is doing. When, for example, we write this function here, we don't even need to write those functions to know what they do. Because we know the structures we're using, we know the data we're using, we know what we can do with it. So I hope this answers. So I mean something like description, blah blah blah. So basically you're talking about Doxygen and JavaDoc and uh, inline documentation or online documentation. Um, I really don't like it. I have to do it at work because it's policy, but for my own projects, I consider them duplication, and I hate duplication. I really hate duplication, so I consider them bad. What I tell developers is to directly refer to the header file, and I do open source because when the header file is not enough, people who need even more details can just refer to the implementation, and then we can cooperate and decide what needs to be part of the specification or what is implementation defined and might change, so the user cannot rely on it. This is, I think, much better than closed proprietary code with Doxygen that just repeats what the code says, which is completely useless. But so I don't know, it's fashion. I'm very surprised at the amount of work which is done because others do it this way, and not because it's actually useful and pragmatic to do it that way. So, but it's a constant, I think, and it's not specific to programming. Okay, so this is really where the tricky code is going to be.
Because we're trying to find the point at which we split it, I guess.
I'm not sure I understand this condition though, because basically, again, check for errors first. So this wouldn't be an error, except that, well, you could consider that splitting a block that is too small would be an error, in which case you don't want to check that condition, you want to check the reverse. If the block is too small to be split, you don't split it.
See.
See?
Uh,
It's already checked.
how do you mean?
I mean that this could return null. If the
Mhm.
block is too small, this would return null, and if it's null, it will not be added to the free list because there is no second block. So when you implement block split here,
Yeah.
the first thing you need to check is the size, but you don't want to write the code here on the second indentation level. You want to write it on the first indentation level because that's where people are going to assume the main code is. So here, you check the error first.
Ah, right. Okay. Um, and adding it's later. We're gonna have to set the boundary tags here, right? Um, which first, um, oh, I was still thinking about the footer tags actually, um, which we do not have anymore. So the the size, does that get set at all? Um, there's no place where we actually set the size of the blocks in the boundary tags. But the size, yeah.
I haven't really listened to you. I was answering chat, sorry.
There's
But
nowhere we really set the size of the size in the boundary tag yet.
remember something, remember something. We already have lots of functions, so let's look at what we have. We have block initialization. So we can initialize our new block with this function. Okay. Uh, Boundary initialization makes a block allocated. Okay. So maybe so yeah, here here we do allocate our block. When we remove it here, flist
Mm-hmm.
remove, it is set allocated. But this is, this is fragile because here, as we said, when we split a block, so currently the block must be allocated. Okay, that's a requirement. Maybe we'd want to split 3 blocks. I don't know. I don't see a reason we want to merge 3 blocks rather than split them. So apparently it's a good thing to force splitting a block to work only on uh, allocated blocks. So let's do that first. Uh, yes. And actually, do we have a block allocated? Yes, we do. Okay, the block must be allocated. So this way, when you initialize the second block, it is allocated to, so it matches what we expect, that when we split an allocated block, we end up with 2 allocated blocks. Okay, that's the first thing. The second thing we have is this function that for now was not used and gives you the next, actually it could give you the next block. It's actually, yeah. Whoa. Yeah, I don't know how to use the edit.
Same, really.
I'll get next, I suppose. Okay. Wait, that would be, let's call it next, simply. Okay, so this should work, right? This gives you the block next to the one you have. Okay. So normally with those 2 functions, you should be able to build 2 blocks. Like the one you have is allocated, which means that it's not part of the free list, which means that it's just a block of memory that you can reset completely. It's yours to manage and write, and you can do whatever you want with it. It's allocated. So you just have to create 2 blocks at the right location. If you want me to do it, I can do it, but
It would probably be a little
you
bit
think?
quicker.
Okay.
Yeah.
It would be quicker, but I was interested in how you would actually manage the problem. But I understand it's the complicated part. So yeah, let's do it this way. Uh, oh shit, the license goes over 80 characters. That's bad. I have to change that. Someday, doesn't really matter. So let's keep the structures here. Okay. Split. All right, so we're here. Um, our first block already has the right address because it's the complete block. So it starts at the address of the first block. So the first thing we need to do is determine the address of the second block. And that's not too difficult. We have a size. We could also assert that this size is already, well, it should be a multiple, but let's make sure that it's aligned correctly. And actually, yeah, we could use the macro directly. So aligned. What? Oh,
You're used to them on your
that's weird. It doesn't work.
profile, I guess. What are you doing?
Oh, I don't have the plugins installed. That's why. Um, I'll move them quickly. Well, actually, I could do.
You could, yeah, you could push it, I guess.
No.
Once more.
That's not what I'm saying. I'm just want to copy my Vim directory here.
Oh,
Okay.
right. Okay.
Okay, so let's check P2 aligned. That still doesn't work. Oh, wait, I copied here instead of there. Okay. And now, does that work? Ah, better. So yeah, that's how it's used. And basically it returns true if X is aligned on A and false otherwise. So we want the size to be correctly aligned, right? So this is a block size. Keep in mind, we always use block sizes except when we convert a payload size into a block size. So we don't have to care about that detail anymore. It's a block size. So what we want is like block 2 is again, I have to decide how to do that. Get next. Okay, it's done here. We have two ways of switching from a block to somewhere in memory. We either convert that into a char pointer and then back into the appropriate pointer type, or we use that GNU extension. I've done it once here. I don't want to do it a second time, so we're gonna create a new function for that. So static struct memblock. Block. So what do we want? Um, Actually, do I need to do that? No, no, I don't. I don't need to do that. I already have the code. I can really use it right away. So what I want to do is use this function to get to the second block. And in order for that to work, I need that block to already have the right size here. So let's do that first. Let's initialize the first block with the new size. And yeah, see, this is why it's probably not. Wait, no, I'm saying crap. This is good. The block init function is initialized. Well, it's defined above, which means I can readily use it here without declaring it, without reordering. Um, which is why usually it's best to have the initialization function first and then the rest following. So block size. So here what I'm doing is that I have this big block first, and then I'm initializing a new block at this exact address, just changing the size. The block is going to remain allocated. It was allocated, and it remains allocated because when we initialize a boundary tag, it's allocated by default. Okay, and now block 2 is mem block. Get next. See what I'm doing? First, I set the right size. So I initialize a new block, which has a new size, the size that we want. And then by using getNext, I get the address right after this size. So I point somewhere in memory which is not initialized, which means I'm going to initialize it too. So block 2, and now the size is going to be the total size, which I don't have anymore because I erased it. So I need to save it minus size. Okay. So this is really the size of the entire region, in the entire area. I don't want to use too many terms because we try to avoid synonyms and aliases in code because it makes things confusing. But for you to understand better, I'm trying to, well, yeah, I'm using different words to try to explain better. So the total size is really the size of the initial block, the big block that we want to split. We initialize the first block with its new smaller size, and we find the second block, and then we initialize that second block with the remainder.
Size
Right?
doesn't actually change though, does it?
Hmm?
The size, the parameter size doesn't actually change though, does it? Memlock
It
init doesn't
doesn't.
change, just for
No.
semantics.
What?
The total size, why would you use that? I'm not quite sure.
Well, the second
It's,
block is like it's subtraction. It's 10 minus 3, it's 7. You know? You have a block of sizes 10,
uh,
you allocate 3, remains 7.
uh,
That's all.
Um,
Oh, network error, apparently.
yeah, I see that too.
Yeah, Twitch has been acting weird lately. Let's check the stream. No problems on the stream itself. Okay.
Okay, that works.
So we split it, okay. And so we just have to return it. And normally we're done. So if there is a problem with this, please tell me, anyone in the chat too. Because that's probably the most, well, that function and this one are probably the most tricky of the allocator. So if you, that's probably where you might have questions, and if you have them, now would be a good time. So is that okay for you, Mental Snake?
I'm still sort of on the total size thing, actually. It,
Okay.
uh, so first you just get the uh,
Let's try and make a picture, a really good picture. I don't think I can get that, unfortunately. Um, this is freeing. Okay, so yeah, the problem with these pictures is that they have all the details that might distract you from what I want to say, and that's a little annoying.
you draw it yourself. Do you have
Yeah, I
a
could
program
do
for that?
that, but I don't draw really well. I'm going to use ASCII art because ASCII art is great. So, okay, B tag, okay, uh, something, we don't know what. Okay, this is your original block. Okay, you tell me if something is not clear. All right.
Yeah, yeah.
Okay, and now split. This is what it gives you. So B tag, okay. Then you go somewhere. Then you have another B tag. Then you have header because it's free. Then it goes there. Okay. So this would be uh, block. EA ASCII art. Okay. And this would be block 2. And actually, let's make them point exactly where, uh, well, exactly at the addresses they point in the code. And I'm going to put that next to the code.
Mm-hmm.
Okay. So total size is this. Okay. Then what I do is that I take block and I initialize it with the new size, which gives this. But at this stage, this is still garbage. Okay, we don't know what's in it. So what I
Oh,
do is that I take the next block, and I can do that because now the first block has the right size. So I end up here, and I initialize it like this. Now it still doesn't actually have the header because that part is done later when we call block split. What we do next is that we add it to the free list. And if you check flist add, then it grabs the header and then it sets the prevent the prevent next pointers by inserting it in the linked list, and then it sets the block free.
no. For some reason, I thought uh, the size of the first block had already been set in the boundary tag. So I was wondering why.
Well, no, it's set here.
Yeah,
That's
yeah,
the point.
yeah. So total size is actually for the very first one, just for the very first block you initialize, total size is the size of the heap.
Sorry, what?
For the very first block you um,
Hmm.
split, I guess. The total size for the first time is the size of the heap.
Yeah.
This, yeah, that took a while for that to
Hmm.
register.
But see, I don't need to know that. The code we write is really meant to work on any block,
Hmm.
and it
Yeah,
will work for the first block too. There is nothing special about it.
yeah,
Okay.
yeah. Just
Well,
to
let's
illustrate, like,
let's try it. Let's try the allocator. Let's try to allocate stuff. Let's play with it.
and
So
then
I'm
you can
going
write
to
the free.
close all this. Let's actually build it. So yeah, we have set free. Okay, we need set free, we need set allocated, and we need get block. Yes, that's right. That's right. I need to take care of that. So set free, set allocated is actually quite easy, but I think it's the blocks. Yes, it's the blocks. Okay. So set free is called here. Okay, so we're going to write the functions here. You already have a set allocated somewhere that is actually implemented. No, we don't. Okay. We could also call it clear allocated to insist that it's a flag. Okay. Now let's write those functions here. Wait, no. Oh, wait. That's still a block. Yeah, the keyboard thing is really annoying. I don't know if it's the same for you. I can't maintain a key pressed and wait for it to scroll.
Oh, right. I
Okay.
have no idea.
So it should be here.
Maybe that's something, or maybe a setting in VNC.
Maybe. Okay, so it should be all well and done. And now the last interesting thing before we make it work is this function. So fheader get block. We don't have a single fheader method. Okay, let's write it here in the order in which the structures are declared. So get block returns a block. All right. So in our model, we're basically here. This is the address we get. Okay. This is what gets inserted into free lists. Okay. This node. So what we want is simply to shift it to that address and cast that into a complete block, right? So it's really easy. We only need to know the offset of the header in the boundary tag. And you have something, so that's something you need to know. you have a macro that is called offset off. I think it's a, yes, it is defined as a macro, and this basically gives you the size between the beginning of a type and a member in that type.
Awesome.
See? So return, we cast it into a block. We take the header, okay, which we cast into, again, a char pointer, for example, so that we can do byte arithmetics instead of pointer arithmetics. And we subtract the offset of the member is header, that one, okay. And the structure is a boundary tag. Okay, and just to make the code less, smaller, more compact, I'm going to use a variable. So if you want to write that kind of C code, if you want to write embedded code, system code, you need to be comfortable with these kind of things. You need to know how to jump from one address to another. You need to know, you need to be careful about pointer arithmetics, um, and that's it. It's really, actually, it's really simple. But I understand it might be tricky initially for someone who's not used to it, especially coming from higher level languages which absolutely don't allow this kind of thing.
Yeah, that's what I was about to say. Coming from uh, software engineering, where you generally don't use
Mm.
like this kind of.
So we have initialized the memory allocator. Let's allocate some memory. Let's allocate 2 blocks actually, and I don't know, print them maybe. So it's just test code, right? Let's call it string 1, string 2. Um, so mem alloc. Let's say we want 60, well, let's say 32, okay? Well, actually, let's use, I don't know, 29 and 13, right? This is crappy code, okay? Don't do that. Do we have str copy, by the way? I know we have string, but yeah, we do have str copy. Great. So again, don't do that. This is crappy code. I'm not checking sizes, and I'm using assert, which shouldn't be used this way, okay? But it's quick and dirty code. That's okay. What did I forget to do? Oh, that's right. So something interesting here. When you fail to include the proper headers, the compiler is going to assume implicit declaration of functions. It's a warning, it's not an error. So because it assumes an implicit declaration of function assert, it's actually going to generate a call to a function named assert, and we can check that with a disassembler. Uh, what now? Oh yes. Which I don't see here. So it's probably encoded as part of the ELF format. Do we see assert somewhere here? Okay, we see it here. We see that we have references to a symbol named assert. Like we could also use an M, which basically means name. The U here means that we have an undefined symbol, and the fact that it's uppercase means that the symbol is expected to be global. So, so that's what the linker sees. The linker sees a function named assert, and here it doesn't find the function assert because it's a macro. So your link is going to fail because of that. So what we need to do here is simply to include the right headers. And the other one is string. Okay, so apparently this seems to work, but since we don't free yet, it's very easy to allocate memory and think that it's correct. What's interesting is when you have multiple threads allocating memory and you want to make sure that those threads have really separate memory, and when they free memory, that this memory is not going to keep being used. So you don't want leaks, you don't want use after free, you don't want off by ones, all kinds of errors. So here we're stopped there, which means we can use GDB for simple debugging. Okay, so locals. Okay, so this one is really at the beginning of the heap as expected, which is really good. And this one is plus 40. So remember, we have 32 of payload plus 12 because of our, well, 12. It's not 12 actually, it's
29.
8, I think. We have boundary tag. Wait, oh, it's 12, right? We
Uh,
have boundary tag and 2 pointers. Well, actually, no, the 2 pointers are when the block is free. So only the boundary tag. And the boundary tag is only 4, right?
uh,
I'm not sure we're missing something here. Oh wait, this is actually my code, not yours. Okay. So we have this. Oh, we have allocated. We have the allocated flag. So, like I said, there is a padding of 3 bytes here because of this. So, and even without this, the size of the structure will be aligned to the alignment of the greater member, which is this one. So basically you have 4 plus 1, which is 5, but it must be aligned to 4 because of this, so you get 8. And we have 40 here, and 40 is 32 plus 8, if I'm right, right? So the 29 here became 32 because it was aligned as we wanted it to be aligned. And 32 plus 8 gives us an offset of 40 for the second block. Okay, and you can see here that despite asking for 29 bytes, we get an address which is aligned on 4 bytes. So this address can be used for any built-in type as specified, as required by the specification. So the implementation seems good. We could create a loop, for example, to allocate all blocks and see how the allocator behaves when out of memory for reliability. Let's do that quickly.
mhm.
Actually, we can close this and reuse that window. Well, let's call it PTR. Um, Actually, it's an infinite loop. Good. You saw that there was a slight delay, which is, well, expected because we have, I think, 32 megabytes of heap.
I think
Um,
so.
and apparently we get out of the loop, so at some point memalloc is going to return null, which is exactly what we want. So yeah, that's good. Let's clean that
Cool.
code. Okay. Well, you can check the diff, and if you're satisfied with it, you can commit the code, and I'll merge it in, and we're good for today. So next time, oh wait, are we? Like, yeah, it's late. It's late. Like, I could work on the free function, but it's late, so we'll do that next time.
Okay. Uh, what is this C scope
Oh, that's
about?
because I generated an index. You can safely ignore it. We could add it to the git ignore, by the way, but that's okay. I'll do it. Don't worry. Have you actually checked the diff?
Oh, oops.
We might have left things that we don't want to go into the commit.
Just use look at this, or
Yeah, like this. So basically we simplified the code by removing the footer boundary tag, and so the header boundary tag structure too. We introduced the memo line macro, and we have a lot more functions. Now boundary tags are allocated by default.
use this to blocks rather than tags as well. Yeah,
Mm-hmm.
it seems
It looks good so far. Let's make sure that it's the case until the end, that we didn't left over some debugging stuff or a stupid coding style error. Yeah, no, this looks good, and it's all small functions, normally quite easy to understand, and that isolate the tricky stuff from the rest, which is really what we want. So for me, the code is fine. Okay, so while Metal Snake commits it, next time is going to be two things, and it's going to be me alone, and so maybe I'll stream that on Friday because Metal Snake is busy with exams. I don't know if you finished. Um, so
I
yeah,
had
Friday.
finished exams, but
You have
yeah,
finished? Okay.
yeah.
So next stream will be Friday, and I'll be alone. I will finish the allocator by implementing the free function with merging, the merging of three blocks together, mentioning things about fragmentation on the way, and why we have segregated feed allocators and this kind of stacked allocators too. Um, so fragmentation is a big deal. It's something you need to know about, and especially in embedded systems, consider it when you design your system. Um, but it should be fast. All right. The next thing, and I'm a little. I think it was Michael C that asked last time what was missing in order to play with interrupts. What's missing is that currently, when we have an interrupt, we have a default handler, and the default handler cannot return from the interrupt. Well, it could, but um, if it returned, it wouldn't be very useful except the fact that it returned. Especially, it wouldn't allow context switching. It wouldn't allow handling the interrupt by, for example, looking at the context, uh, printing debugging information about the registers, for example. So that's what I'll be doing. I'll be implementing low-level handling of interrupts in assembly, and I'll provide users with a way to set interrupt handler uh, functions, specific handlers. So, for example, the UART driver will at some point provide a handler that will be called every time there is an interrupt on the UART, so that it knows when to grab a character. These kind of things. And this will be a lot of assembly. and some processor-specific stuff. So data sheets and reading formal documentation, and actually little code. There's not much code except the assembly. In C is very quick.
Something like this.
So mem
Is it
add
okay with
allocation
that?
functionality. Yeah, the second line is really not needed. You
Just like this.
because it basically says what you say in the title. The fact that you implement splitting is really not that relevant. It's an implementation detail.
See if that
So
works.
so again, the rule about commits and comments is that you should comment what the code does. The code splits, so you should comment that in the code, and you should explain what changes in commit logs. So you could say that now you are splitting stuff, but since allocation didn't exist in the first place, it makes no sense. But for example, if I made a first commit with free without merging, and then I implemented a new commit, well, I added a commit that implemented merging of blocks, then in that commit I would say that it implements merging. See, because that's what changes.
Okay,
You comment what is, and you log what changes.
makes sense. I'll do the pull request thing on my side. Hello?
Yeah.
Okay.
Am I supposed to do something?
No, no, no. I just I saw a network error coming up as well.
Oh, oh yes, right. That's annoying.
And it's requested.
Okay. So very quickly. And voila. Excellent.
It,
So yeah, we are on time. It's midnight only. uh, and we basically did what well, yeah, the bulk of what we wanted to do, because I would have liked to start the free implementation, but yeah, it's too late. It's too late. So next time. And we still have 5 minutes if you have questions, but I guess most people are okay with what was done, because we haven't had questions for some time now. Also, I think people left because of the network error thing, which is
yep.
weird, because I have no drop frames here. So it's really on the side of Twitch, not mine. So yeah, if you guys have questions, want to discuss things, or even you, Metal Snake, of course, um, we have a few minutes.
So what this is the memory allocation uh, algorithm is a first fit, right? Just to
So I'm not sure about the names. I need to find them, but I think you're right. I think it's first fit.
going
Okay,
by the
this is
name
too
makes
complicated.
sense.
Memory allocation, first fit. So, um, yeah, so I remember, I think I still have it somewhere. Let's take a look. A very interesting paper that now is quite old, but very, very interesting. not mounted. So I think it was in Solaris, extending the slab allocator to many CPUs and arbitrary resources. So this paper describes one of the most complex structure for a memory allocator because it's actually a stack of a a, a normal regular slab allocator, which is already quite complicated. We'll talk about that next time. But in addition, it adds an integer allocator to allocate addresses, but not only addresses. It can allocate any integer, and it's quite effective at that. But it's really complicated. I decided not to use it in my own system because I don't have those needs, and there is a cost. Um, so yeah, they have the slab allocator, which dates back from 1994, I think, or 96. I don't remember exactly. I think it's 94. Magazines are the per CPU structures, and then you have VMEM, the fast general resource allocator, so integer allocator really. And that thing here supports multiple policies, if I remember correctly.
What do you mean by integer allocator? What does that
How
mean?
do you allocate a PID, for example, a process ID?
Okay.
See, it's not memory; it's integers, and you want to be sure that you don't return a PID that is already used, and at the same time you don't want to check all the PIDs to make sure that they're not used because it doesn't scale. If you have 1,000 processes, it's going to be slow. So you see, it's a real problem.
Yeah. Yeah.
The way it's done in Linux and in many implementations today is that we use radix trees for that, except that instead of storing something in the trees, we just store the keys themselves. So basically, if we have a slot somewhere that is not like if you have a bit in a bitmap, which is 0, it means your entry is free, so you can allocate the matching integer, and otherwise you know that it's allocated. And the code in Linux, if I remember correctly, is ID. So you have IDR. They used to have IDA. I don't know if it's still there. Okay, yeah, IDA. That's it. IDR-based ID allocator used when translation from the ID to pointer isn't necessary. So basically, it's really meant for IDs and nothing else. So here, if I remember correctly, maybe it's not here, but I'm pretty sure it's here. Yes, that's it. So you have policies. You have best fit, instant fit, and next fit. So it's not first fit because first fit probably predates that, and the paper wants to extend what exists, but it's very close. Um, Best fit uses the smallest free segment that can satisfy the allocation. So yeah, the goal is to minimize fragmentation. So the problem with that way of doing things is that you have to walk over all the existing blocks, right? All the
Yeah.
free blocks, more precisely, and you take the smallest one that matches the size you want, which means complexity is O1. So the more free blocks you have, the slower it's going to get. It's expensive. It's very expensive, but at the same time, if you want to minimize fragmentation, you are going to need to pay some price somewhere. Then you have the opposite, instant fit. So here it provides a good approximation to best fit in guaranteed constant time. So basically what it does is that it takes the list that is uh, right above the requested size. So here it's a segregated fit, right? So imagine that all size you have are ranges between powers of 2. So for example, you're going to have 4 to 8, 8 to 16, 16 to 32, 32 to 64, etc. So if you want to allocate 20 bytes, if you take the list that matches the sizes between 16 and 32, you might not even succeed. For example, this list might be filled with blocks of size 16, and you can't put 20 bytes in 16 bytes. So in case it doesn't work, it's going to go to the list above, and I think that's what NextFit does. But instant fit here, what it does is that it directly goes in the list right above what you want. So basically, you ask for 20 bytes, it's going to directly look in the list with 32 bytes, and therefore, as soon as it finds a free block, and actually, if there is any free block, if the free list is not empty, you know that the block is going to be usable for that request. So that's why it's instant, guaranteed constant time. You know that as soon as there is a free block in that list, it works. The number of operations doesn't depend on the number of free blocks you have. And then you have next fit. So this one is what use the next free segment after the one previously allocated. Okay. So basically this one is like, well, this one is just, it uses a hint. Instead of starting from the beginning of the list, it starts from somewhere in the list, which is a cached pointer from the last allocation. It doesn't really matter for, much. So these are policies that I knew about from here. Um, there is another paper which is also really, really good. Um, where is it? It's this one. It's quite old now. Dynamic storage allocation, survey critical review. Yeah, you can see that it's all just by looking at the fonts. Wow, it's actually unreadable. I'll have to find a better version. And this one lists lots of allocation policies, and I'm pretty sure that you're going to find first fit and all, well, most of other algorithms in there. So first fit, worst fit, best fit. So best fit we already described, right? The smallest which will fit. Okay. Worst fit, this one is the largest block, and first fit is the first we find. So yeah, the one we implement is that one. Yeah, clearly.
Yep.
Okay, so this one is Goki 97. The one I have is not referenced here. That's weird. Anyway. Okay, well guys, thanks for watching. So see you Friday, and that's it. Good
Yep.
night.